View of the structure of the cell membrane. Let's just revise ourselves of some of the important functions. So the cell membrane allows for transport of certain materials from the intracellular fluid to the extracellular fluid. Now we talked about these two fluid compartments way at the beginning of the semester, and having the plasma membrane, having the unique structure of the phospholipid bilayer is important to allowing the exchange of this material. Also important to note is that the membrane is selectively permeable. So there are certain materials, certain ions that can cross, and some that cannot cross. There's certain particles that can cross and some that cannot cross. Okay? And we'll talk about the difference in those in a minute. All right, so importance of transport. All right, why is it important for the cell membrane to allow certain things to cross? Why is that important? Why is it important for the cell? Why isn't it just a big brick wall or a rigid structure that allows nothing through? Why is that not the ideal scenario here? Why do we need transport? Okay, perfect. Thank you. So sometimes you want to bring certain important substances in, like oxygen, like nutrients, like water. And sometimes you want to get rid of certain processes, or certain substances, sorry. All right, so there's carbon dioxide, which is a byproduct of cellular respiration, and nitrogen. You want to get rid of nitrogen as well. Okay, and we talked about last or Monday, the importance of bringing oxygen into the cell. So what was the importance of having oxygen come into the cell? Just to review what we talked about.
Just a binder here for the electrons.
Right, so it acts as the electron acceptor, right? Perfectly cellular respiration. So oxygen is important as the final electron acceptor of the electron transport chain. Okay, so we also said that membranes are selectively permeable. So they allow certain molecules to pass through and others do not pass through. Now, this can be dependent on charge, this can be dependent on size, and this is restricted, right? This is restricted. Not everything will go through the membrane. This would create a leaky membrane, and this is not what we want. Okay, we want a very select or restrictive movement of certain molecules through the membrane. Now, non-polar molecules can cross the membrane, right? Non-polar molecules, why is this? Why can non-polar molecules cross the membrane? And we talked about this a little bit before. But just to recap it, why can a non-polar molecule cross the membrane?
Because the internal part is non-polar.
Right, so the center is non-polar, and so only a molecule, right, that is non-polar or hydrophobic can traverse that hydrophobic center, right? It can easily move across the membrane. Examples are oxygen, carbon dioxide, fatty acids. Okay? Now, ions and polar molecules normally do not go through the membrane. Now, there's an exception here because water can move across the membrane, although it is polar. But this is size dependent. So because of the size of water, it's a very small molecule, it will go through the membrane. But normally, water, ions, and other polar molecules cannot traverse the membrane. Examples of these are glucose, right? Glucose needs a transport in order to enter the cell. We'll talk about the glucose transporter, right? Certain proteins cannot just move across the membrane. Sodium and other ions, potassium, chloride, they cannot just move across the membrane. They are going to require ion channels, which we'll talk about, or proteins, other mechanisms to assist them entering the cell. Okay? So traditionally, non-polar molecules or smaller sized molecules can traverse the membrane, whereas polar molecules and charged particles, such as ions, cannot traverse the membrane. And that's part of the selective permeability. All right, so that is basically the structure of the membrane, the function of the membrane, and the two important features that we want to point out: the selective permeability and the transport that occurs across the membrane. Okay? Let's look at lecture objective 2. And this is where we will explain the role of chemical, electrical, and electrochemical driving force in the passive transport of substances across a membrane, and we'll distinguish between passive transport, which is spontaneous, and active transport, which requires some type of energy input. It's not spontaneous. Okay. Now let's talk about some factors that affect the direction of transport. Okay, and in this little scenario that we have here, there's a hill or a slight incline, and there are two balls. There's an orange ball, there's a green ball. Now, one of these balls is going to move much easier than the other. Which one of those balls is going to move easier? I'm hearing orange, right? So orange, and that's correct, right? Orange is on the top of the hill, top of the incline. And so with very little effort, with no energy input, you can move the orange ball down the hill. The green ball, not so much, right? We're going to need some energy input in order to move this ball up the hill. And this is an example which highlights passive transport, which is spontaneous. And that's going to be a downhill movement. That's going to be most favorable or the easiest. And then there's active transport, which is not spontaneous. It's going to be going against what feels most natural or feels easiest. Okay, that's going to require energy input or ATP input. Okay, so spontaneous or passive transport is spontaneous, requiring no energy, and active transport is not spontaneous and it does require energy. All right. So driving forces that affect the movement of particles across a membrane include both chemical and electrical forces. So we will describe chemical driving forces, or the chemical driving force first. Then we'll talk about the electrical driving force. And then we will put both of those forces together for the sum, which is called the electrochemical driving force. Okay? Both of these forces combined equals the electrochemical driving force. Now this can be passive, moving down the force. And when we say down the force, we mean moving with that gradient, right? Which is spontaneous and not requiring energy. Or it can be active, moving against that force. Okay, well, this will describe your question.
Yeah, so passive always means with the gradient.
Mm-hmm. Passive meaning moving down the force or down the gradient. Active meaning moving against it. Right? So this requires energy. It's about you trying to push a barrel up a hill. You're going to require some sort of energy input to get that up the hill. As opposed to pushing it down the hill, you require very little energy. Okay, so let's start by looking at the chemical driving force. Now, the chemical driving force is the understanding that certain concentrations, like difference in particle concentration, creates a concentration gradient. All right, what is a concentration gradient? What is a concentration gradient?
It's where like one side has more than the other.
Mm-hmm.
The higher side will flow to the other.
Perfect. Perfect. So we have one side of the membrane having more of a certain particle than the other. And so the natural inclination is that the particles will flow from an area of high concentration to an area of a low concentration. And that is the force that is responsible for this movement, the chemical driving force. All right, so it's dependent upon a concentration gradient. And the gradient basically pushes particles from where they're high in number or high in concentration to where they are lower in concentration. Okay. So let's talk about this. Oops. Let's talk about the chemical driving force here. Can you see this? Okay, the chemical driving force. Now, in the chemical driving force, right, this force is moving down a concentration gradient. And we already described what a concentration gradient is. Right, so this is the force that is moving down a concentration gradient. So it's going to be moving from a place of high concentration to an area of a lower concentration. Or low. Alrighty. So let's illustrate this here. We have a cell. Let's draw a little nucleus. All right, so this is our cell. This is our cell membrane. And we have two particles interacting across this cell membrane. So we have particle A and particle, particle A and particle B. Okay. Now, on the inside of the cell, let's say we have lots of particle B. And we have very little particle B on the outside of the cell here. Okay. And the reverse is true for particle A. We have a lot of particle A on the outside of the cell. And then very little particle A inside the cell. Okay. Now, what do we think is going to happen naturally here, given what we just said, given the chemical driving force? What is the effect of this force on the cell? What's going to happen?
It's gonna want to even out.
It's going to want to even out. So what will have to happen in terms of particle A and B?
Particle B is going to diffuse out of the cell. Particle A is going to go into the cell.
Perfect. So particle B, which is in higher concentration inside the cell, is going to want to leave the cell, right, under the influence of this force. Okay, and then the opposite is true. Particle A outside the cell is going to enter or want to enter the cell. Okay, and this is the chemical driving force here. So if we were to look at the gradients inside and outside the cell, right, let's say inside the cell and outside the cell, right? Particle B is highest inside the cell and lowest outside the cell. Right, so that's the gradient for particle B. Particle A is the opposite. It's highest outside the cell So this is our gradient for particle A. Okay. And so the movement that we want to take place is particle B would try to move outside the cell, going down its concentration gradient. And particle A wants to move inside the cell, going down its concentration gradient.